I'm a mechanical engineer at Sarah Metchard, and my company, Staengl Engineering, is based in Virginia. And we've been committed to sustainable design since our inception, but we discovered or were introduced to Passive House about 15 years ago, and it really changed our practice from one where we were focused on the systems to being more focused on the building as a whole and really working to simplify and downsize our mechanical systems. So I'm going to talk about that a little bit today. And the other thing I wanted to mention is that most of our work is multifamily residential or non-residential building types. But the principles that I'm going to talk about really apply to all building types, including single-family residential. So, as many of you know, Passive House had its origins in the U.S. The super insulated Saskatchewan Conservation House was designed in the U.S. and included super insulation for its time, passive and active solar collection, and air-to-air energy recovery ventilation. Many of the passive solar houses of the 70s did not have any active heating or cooling. So while the inside temperature stayed relatively constant, there was no thermostat and no easy way to actively control the temperature. The PHI Passive House system was designed around the concept of tunneling through the cost barrier, which was coined by Hunter and Amory Lovins. The idea being that if you continued to add insulation beyond the point of diminishing returns, you could get to a point where a dramatic cost reduction would occur by eliminating a system. In Germany, this typically meant elimination of a boiler or a hydronic heating system, and according to their rigorous studies, led to a life cycle cost minimum in the building project. The architects of the Passive House system decided that it still made sense to provide some heat to the building in order to allow occupants to control the temperature of their environment. There are several ways to do this, but an elegant approach is to put a bit of heat into the ventilation air, which is already distributed around the structure to provide ventilation where it's needed. In the example case above, we would need approximately 86 CFM of ventilation air to provide the required heat for the building, which is a reasonable amount of ventilation air for a 1,200 square foot house, depending on how many bedrooms and bathrooms you have and the required kitchen exhaust. So if we use the maximum heating load metric, which is for the PHI system was 3.14 BTUs per square foot per hour. We come up with a load of about 3,800 BTUs per hour, which can be met with the ventilation air heated to about 95 degrees Fahrenheit. But it's important to recognize that in Germany, where the Passive House system was developed, there's seldom a need for air conditioning. You can see there are relatively few hours that are above the 75 to 80 degrees. There's also no need for dehumidification in most cases. Most of the year, if any cooling is needed, it can be done by opening windows to bring in cool outside air. So let's look at a project in Seattle. Seattle's climate is similar to Germany. There are very few hours in a typical year that are above 80 degrees. Humidity in the summertime is also relatively low, so dehumidification is not typically required. The Madrone Passive House is a project that's recently finished up on 24th Avenue in Seattle. It houses 107 apartments, most of which are small efficiency dwelling units or SEDU units. While the building has small SEDU units and about 20 one-bedroom apartments, we'll look at the one-bedroom units as the worst case. The largest one-bedroom units are 385 square feet. Running loads on the building, we find the one bedrooms to range from approximately 1,000 to 1,500 BTUs per hour in heating load. The heating loads assume there's no activity in the apartments. We're not taking any credit from occupants, heat, light, or other equipment. This is to make sure that we're looking at a worst case scenario. By code, the apartment only requires 30 CFM of ventilation air because we are continuously exhausting the kitchen and the bathroom. We require 45 CFM of continuous exhaust. To balance the exhaust, we're providing 45 CFM of air to the apartment. If we heat that ventilation air to 95 degrees, provides 1,350 BTUs per hour of heat to the space. Taking credit for one occupant, we've met the peak load from just by providing heat to the ventilation air. However, in order to make sure everyone has a thermostat in the building, we chose to provide electric heat in each apartment. This allows occupants to control their own temperature at the apartment level. So we put in small cove heaters at very modest cost to the project. On the heating side of things for this building, we're able to provide all the necessary heat through the ventilation air, but are giving the tenants small electric heaters so they can control their temperature. So far, so good. This image shows the ERV on the roof. A small heat pump post-conditions the ventilation air to cool it to 55 degrees when conditions are hot outside. This provides 1,000 BTUs per hour of cooling to each apartment, which meets the cooling load under most conditions. We analyzed the potential for overheating in the building to evaluate the need for additional cooling in the apartments. Based on the exposure and the shading, most of the apartments remain comfortable for most of the year. However, because of the windows and the exposure of some of the units, the owner decided to add air conditioning to some of the apartments. In this case, small ductless heat pumps were added to 12 of the apartments that were vulnerable to overheating from solar gain. For the rest of the apartments, cooling supplied only through the ventilation air. So that's how it can work in Seattle. But what about the rest of the country? Climate conditions vary widely across the US and Canada. Can we apply the same logic to the varied conditions across the US? Generally, Passive House allows us the potential to eliminate a system in cold climates or climates with strong diurnal swing in the summertime. Additionally, evaporative cooling can be applied where the summer is dry. But what can we do in warmer, more humid climates? Because of the need for cooling and dehumidification in many of the US climate zones, it's often impractical to eliminate a system as we can in Germany. But the same logic applies. We can apply rigorous design principles to take advantage of the well-insulated, tight Passive House envelope and to downsize and simplify the mechanical system. The objective being to shift costs from the systems to the building envelope and thereby invest in the parts of the building that have a longer useful life, increase comfort, and reduce the life cycle cost of the building. There's some basic design principles that apply to most system types. The first is just making sure that the equipment is right size and using realistic loads that take advantage of the well-insulated, advanced too quickly there, of the well-insulated airtight Passive House construction. So this slide shows a comparison of two similar multifamily projects with studio apartments. The project on the left used 2 wall-mounted indoor units to serve the apartment, one in the kitchen area and one in the living room. And this resulted in an increased outdoor unit capacity and a huge increase in equipment costs. The project on the right used one 6,000 BTU per hour wall-mounted unit for the apartment, which was still oversized compared to realistic loads, but was the minimum equipment size available at the time. So we use a metric of square feet per ton to evaluate how much mechanical capacity is needed for the building. And using this metric, the FIA certified building required 26% of the capacity as compared to the code building. And both of these are real projects that were constructed. The cost wasn't 25%, it was about half, but it was a significant cost reduction in the mechanical equipment for the building. So another important design principle is low static pressure design for ductwork and equipment, and minimizing the ductwork in the systems. Residential HVAC systems and commercial HVAC systems typically supply conditioned air at the perimeter wall near the windows. In fact, some housing authorities mandate this approach because typically double pane windows are uncomfortable when it's really cold in the wintertime. So the approach is to wash those windows with conditioned air. But the passive building insulation creates a comfortable environment without the need to wash the windows with conditioned air. So to take advantage of this, the system should be simplified and minimized to reduce fan energy and first cost in the system. Another important design parameter to be aware of is that beefing up the building envelope in a passive building shifts the balance point to a cooler temperature. The balance point is the point at which any building shifts from needing cooling to needing heating. And for typical buildings, that's often in the range of 55 degrees, but for a passive house, it can be much lower. And it's also can be exacerbated in denser buildings and buildings with 24-hour populations. So this might seem like a liability, but it's actually a benefit because when we shift to cooling at a lower temperature, we can cool directly with outside air, and informs how we should design our systems, and also allows us to cool just by opening windows. Another important consideration is humidity control. A lot's been said about the problems associated with humidity buildup in tight, well-insulated buildings. This is because insulation and shading reduce the cooling load in these buildings, so the air conditioners run less often, which allows latent loads to go untreated and humidity can build up in the space. It's important to recognize that for most building types and most climates, the majority of the humidity load comes in with the ventilation air and from infiltration. We know that passive house buildings have greatly reduced infiltration, so the biggest source of humidity is often the ventilation air. And this is especially an issue in mixed humid and hot humid climates. For this reason, it's often most economical and energy efficient to treat humidity by drying out the incoming ventilation air. The ERV will moderate the humidity, but it's often helpful to provide additional cooling to dry out the air before it's introduced into the building. And this can often eliminate the need for costly and inefficient dehumidifiers inside the building. So in climates where cooling is required, an inexpensive and popular approach has been to use small split heat pumps to condition the building. This project was a FIA certified building in Pittsburgh. The project used split heat pumps with minimal ductwork to serve each apartment and neighborhood style ERVs for the ventilation air. In spring of 2020, the mechanical portion of this project bid out at about $17,000 per apartment, which is not too bad for a project that required full air conditioning. However, additional complexity has recently been added to the use of split systems or VRF systems due to the new refrigerant change from R410A to R32 and R454B, which goes into effect next year. Because the new refrigerants are flammable, there are strict requirements related to running refrigerant piping through a building. This detail shows a shaft that's needed to run refrigerant piping vertically through a building. And the shafts need to have exhaust fans and refrigerant sensors. And you can see on the plan the number of shafts that would be required in this building. So it's easy to see that these shafts are going to be costly and will represent new challenges for passive house buildings to meet air sealing requirements. There's also kind of a constructability issue associated with these shafts, and that is that because of the class of refrigerant, the refrigerant piping has to be inspected. So the shafts have to be built on 3 sides and the refrigerant piping installed and then inspected, and then the shaft gets closed up. So it's kind of a hassle. A new approach, which is gaining popularity, is the use of all-in-one style pieces of HVAC equipment. There are several pieces of equipment on the market that combine heating, cooling, ventilation, and dehumidification in one device. The hope is that these units will drive down system cost and reduce on-site labor by reducing ductwork and equipment installation labor. Additionally, they address the refrigerant issues as all of the refrigerants combined within one device, and there's no site-installed refrigerant piping running through the building. There are several manufacturers bringing these products to the US and Canada. Some that are currently available are Minotaur and Efoca. The Minotaur unit's a compressor-based device that does heating, cooling, ventilation, and dehumidification. And Efoca has a vertical all-in-one heat pump that heats, cools, and ventilates through an integrated energy recovery ventilator. These systems offer some unique advantages in multifamily construction. They combine all of these features in one device, potentially saving install and maintenance costs. Both of the pieces of equipment are self-contained, so no outdoor equipment is necessary, which can free up roof space for occupancy or solar panels. Condenser air is ducted from the outside and exhausted back out. So this is another project in Pittsburgh that's just finished construction recently, where we did use the Efoca AIO all-in-one heat pump. It was very similar to the Emerald Hills project. And the intent was to reduce HVAC system costs by greatly reducing the need for on-site ductwork and installation labor. The unit heats, cools, and has an integrated ERV to continuously exhaust the bathroom and kitchen and provides continuous fresh air to the space. One issue we discovered with this first generation all-in-one unit was that the louver that the manufacturer recommends for the outside air intake and exhaust was significantly undersized. Using custom louvers forced us to separate the intake and exhaust, which added ductwork to the job. Efoca has addressed this issue with their second generation unit that's coming out shortly. The contractor felt that time and cost would be saved by having prefabricated metal closet made offsite for the unit, which didn't really work out as well as intended. So in the future, we would likely recommend building a framed out closet for the unit or mounting it into a thickened wall. These are some examples of mechanical systems for passive housing projects in different climate zones. While it's more challenging in warmer, more humid climates, if we hold to the objectives of downsizing and simplifying the mechanical systems, we found that we can reduce the system cost to channel investment into the building envelope. Thanks, and I'm happy to answer any questions.
Thank you, Galen. Especially, when we were just kind of talking about how hot it's getting in the summer, and especially in the Pacific Northwest, people panic buy their ACs and whatnot. I think this is a nice relevant topic. So I would love to throw it to Zach to thank our sponsors, because we have a couple really good questions, but those of you that got to sit through this meeting, or those of you who have just joined, try to reflect and see if you have any other questions. And this is a good time to ask right after Zach thanks our sponsors.
All right, great. Let's see. I think we need to spotlight. Can people see this? Hopefully people can see the image on my screen. Thank you. So a big thank you to our sponsors who make everything possible here at Passive House Accelerator. So thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you to our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Glavel, Minotaur, Partel, Rockwell North America, Stocorp, and Zola Windows. And thanks to our champion sponsors, Bewizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050. And thanks to our patron sponsors, Brennan, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Longboard, RDH Building Science, and Sanderson Sustainable Design. Thank you, sponsors.
Awesome. Thanks, sponsors. We love you guys. Alrighty, y'all. I have a couple questions in our queue here, and what I'm going to do is ask you if you would like to unmute and ask your own question. If you're either gone or if you would not prefer to do that, I can totally ask it for you. But let us start out with George. Oh, and you know what? Before we start off with you, George, we have a poll that just popped up here. Hopefully other people can see that. If you can take a quick moment to answer this poll, that would be awesome. It looks like there's about 5 questions.
Yeah, thank you. And I think we can let those
Absolutely.
answers happen in the background as you go.
Awesome. Cool. That looks like some cool questions there. Alrighty, George. I have a question that came in from you first, if you would like to unmute and ask your question. Otherwise, I can ask it for you. I'm going to give you a couple seconds to race to your unmute button. And looks like I beat you to the unmute button that I've already unmuted. Alrighty, George. George's question is, why not use CO2 as a refrigerant instead of flammable R32?
Absolutely. The issue is we don't have any CO2 based air conditioners yet available in the US, but we have lots of CO2 heat pumps that make hot water. So, you know, if we're just looking to heat or make hot water, that's a great way to go.
Okay, interesting.
Can I do a quick follow-up on that question on that? Galen, what is your sense of how the kind of trajectory of evolution of refrigerants looks like? Is that likely to change soon, you think, or what's your sense?
So I'm not completely aware of what the technical challenges are to bringing a CO2 air conditioner to the US. I do think that this current refrigerant change that sort of jumped up on us to get rid of R410A, which makes total sense because R410A has a very high global warming potential.
Yeah.
You know, the solutions are basically R410A mixed with a flammable refrigerant. So my expectation is that those are going to have a fairly short lifespan as well. And, you know, probably in 5 or 10 years, we're going to be phasing them out for something hopefully much better.
Right. Yeah, excellent. And this is just to provide context to folks who are new to thinking about refrigerants. This is also within the context of the global Montreal Protocol, where there was some really great progress a few years ago with a global agreement to reduce the global warming potential of refrigerants. So there's a drive everywhere to improve these numbers around global warming potential.
Interesting. It's going to be interesting to see how this really comes to fruition as they phase in and out, honestly. Alrighty, Galen, I have a question for you, and it's kind of about the IFOCA unit. And we're wondering if the sound was the issue with the metal enclosure for the IFOCA unit. Do you happen to know and have any insight on that?
Yeah, we were worried about sound and just static pressure because I think when they released the AIO, they were just reusing a grill that they had for smaller pieces of equipment. And when we looked at the pressure loss across the grill, it just wasn't going to work both from a sound and static pressure perspective. So that's what forced us to put it in custom grills.
That's interesting. Alrighty, thank you for that.
Hey, Doug Hogan, sorry to interrupt again, Sarah.
You're fine.
Just to continue on the refrigerants path, Doug Horgan from Washington, D.C. shared that CO2 can't phase change at temperatures over 88 degrees, so it loses a lot of efficiency in warm summer temperatures. So thanks for that insight, Doug.
Yeah, thanks.
Yeah, it's good to know. I didn't know that. Alrighty, so up next I have Peter. Peter, you asked a question. Would you like to unmute and ask it out loud if you're still here?
Yep, I'm still here. Galen, you
Awesome.
mentioned that there's a new EFICA unit coming out that I think you said addresses the 10-foot separation of the ductwork. Is that, or the grills, the intake and exhaust? Is that accurate?
So what the code says on that is that you're allowed to not have a 10-foot separation if there is a manufacturer supplied grill that they have tested in order to show that there's less than, I believe it's 10% recirculation. They've come out with a second generation EFOCA unit, which has larger connections for the intake and exhaust, and we anticipate that they're going to be supplying it with a larger grill as well.
Okay, thank you. So yeah, the 10-foot separation can be a bit of a challenge sometimes. So thanks for that.
Yeah, and the issue with these all-in-one units is that you know, it's mostly condenser air that we're bringing in and exhausting, right? Only a small percentage of it is ventilation air, which is what applies to the 10-foot separation. So unfortunately, the way the code is written, it has to be a manufacturer supplied grill in order to get away from that. But I think other folks have also been successful in just getting waivers because they argue that it's only a small percentage of ventilation air. It's mostly just condenser air. Does that make sense?
Yeah, thank you. I'm in Minneapolis. We're looking at our first project, the 21-story building, and we're putting in the EFICA system in addition to the existing baseboard in order to get the ventilation without getting into the 410A refrigerant challenge. And that separation opened my eyes, so I'll pay attention to that.
Yeah. Yeah, you might be able to get a waiver if you talk to your local inspector.
Okay, thank you.
And there is precedent for that.
Thank you.
All right, good information. Thanks for answering that, Galen. All right, I have George again. George was doing a great job answering the poll. So George, if you would like to unmute and ask your follow-up question, and this time I won't beat you to that unmute button. Feel free. Otherwise, I'm gonna go really slowly. And maybe I will still beat you there. All right, George, I'm gonna ask your question for you. Feel free to jump in and interrupt me though, if you'd like to.
Hi,
all right.
sorry, I'm back and forth between the chat and looking at you and having access to the mute button. So
Totally.
I noticed there's been a lot of enthusiasm about the heat pumps, and I also noticed this flammable refrigerant issue, and the possibility, well, the reality that the heat pumps going in now are using refrigerant that's going to be obsolete. Now I assume that those are going to be supported going forward, but I think we all think about and hopefully analyze life cycle carbon, and if we have a major piece of equipment to the tune of $15,000 going in, we wouldn't want that to be obsolete in 1 or 2 years. So I just wondered, what about this transition from one refrigerant to another? And is there any other option other than these flammable refrigerants if we're trying to get down to less greenhouse gas impact of the refrigerants themselves, assuming they will leak in one way or another?
Well, I will say that the industry is in chaos with this refrigerant transition. And because I think it's been coming for a while, but just like anything else, the industry was in denial until the EPA actually made a ruling, and so now everybody's scrambling to get their new equipment listed and all that. I think ultimately for larger buildings and maybe for smaller buildings as well, I would like to see us move back to hydronics. Because then we create buildings that are somewhat future-proof, right? If you're distributing in the building with water, then the device that makes that water hot and cold is something that you can change out as the technology changes. The problem with hydronics is that in most markets, it's a premium service. So it's hard to get it to be cost effective, but as a whole, I would like to see the industry move back in that direction.
And are you fine using polyethylene glycol in hydronic systems so that the loop to the outdoors can be used, or is that a problem?
No, yeah, if you're in a freezing climate, you need some antifreeze for sure.
Thank you. I love that answer.
Awesome. I love that you love that answer. All right, we have up next, Aaron. Aaron Yassine, would you like to unmute and ask your question if you're still on the call with us?
Sure, I'm still here. Am I unmuted?
You sure are, Aaron.
Galen, fantastic presentation. I'm curious, your perspective. You've been doing this for so long. Where do you see the technology going? As one part of the question, where would you like to see it go? What do you think is the most urgent technological advancement that could happen in the next 12 to 36 months that you've been really looking for years now?
So, the all-in-one pieces of equipment are something that we've been wanting for a while. And it's certainly in multifamily construction where, apartments are small and in a passive house, the loads can be very small. We want right-sized, simple equipment that can handle ventilation, air, and humidity as well. We're starting to see some of that equipment come onto the market. Another important factor for this equipment is that, if we're penetrating the outside wall, it needs to be done in an airtight, reliable, airtight way. And that's also a challenge. The small right-sized pieces of equipment that we can kind of plug and play, I think that's where the industry is going.
So that would really be units that can be just kind of sized for each. If you're doing a multifamily, for example, for each apartment, right? So you're not talking about, so it can really be localized.
Yeah.
And then that can be distributed. So there's a lot of design flexibility that's capable in the process.
That's right.
Yeah, that makes perfect sense. So do you think we're going to get units that you'll be really happy with in the next 12, 24, 36 months?
Yeah, there's some products starting to come into the country. Unfortunately, there's not really enough of it yet to get good competition, but hopefully in the next 2-3 years, there will be.
Great. Let's hope it happens.
Fingers crossed. Alrighty, next in the question queue, I'm gonna go ahead and ask it to you, Galen. What are your thoughts on passive ventilation, especially in taller and larger passive house buildings? Is there any future where we bring back the ancient methods of ventilation and passive cooling?
Yeah, absolutely. I think I feel like passive house, has sort of gotten a reputation, or early on got a reputation because a lot of this example projects coming out of Germany were very utilitarian. Box-like small windows, close it up and ventilate it. But it doesn't have to be that way, right? I mean, it can be a building that when conditions are right, it opens up and uses natural ventilation, but then is able to close up again when conditions are hot or cold. I think there's no reason why, it has to be a simple box with tiny windows.
Sweet. So basically one giant damper as the envelope. Why aren't we just making them like that? Alrighty. That's a pretty good. I'm just really curious to see like where the future is going to take us in the passive, world, and how we start to see some of these kind of become more simple and yet do a whole lot more than they might be doing right now. Anyway, we have another question up in the queue, and it's from Doug. Doug, would you like to ask your question? Doug Horgan, if you are still on with us.
Yeah, sure.
Awesome.
I know you're allowed to use flammable refrigerants in small quantities in refrigerators and stuff like that. Does that apply to the all-in-one, the Minutair, and the FOCA type package units?
Yeah, there's a quantity in the code above which you have to have a refrigerant sensor with an alarm. I believe that most of those units are below that quantity. But the code for the flammable refrigerants, it allows you to move refrigerant piping horizontally in the building without shafts. But when you move vertically, you have to put it in a shaft with a refrigerant sensor. Actually, to be technically correct, you don't have to have a refrigerant sensor if you make it a naturally ventilated shaft, but we can't get our head around how you could possibly do that in a passive house, basically have an open shaft running through the building, 20 or 30 times. It sounds totally crazy now, so.
Alrighty. I have my next question from Enrique Bueno. If you would like to unmute and ask your question, that is awesome. If not, I'm totally happy to ask it for you.
Hey, Galen, thank you for the presentation. Great.
Hey, Enrique, good to see you.
How are you doing? The Minutair is not Passive House Institute certified. Is the reason why it hasn't been certified the mentioning of your in the presentation that the efficiency is reduced because of not having an ERV core?
I think you should talk directly to Minutair about that, but I know that there has been discussion about that because the energy recovery requires the compressor to run, so it's not as efficient as with a passive core. So that may be the issue from their perspective.
We have seen here a great increase in energy consumption during the winter time for the Minutair. Is that has there been any comparison between ERV's cores and Minutair?
So the first generation, or the Pentacare V12 of the Minutair, the heat pump does not operate well at low temperatures, and so you do need electric resistance heat for low temperature operation. So if you're putting it in a cold climate, you will see pretty high energy consumption in the winter time. I am hopeful that they're going to address that with their new next generation unit.
Yeah, I think they modified that and reduced the dehumidification capacity by doing that. So,
yeah.
Okay. Thank you.
Good to see you.
Thank you.
See you.
All right, I have one other question that I'm gonna ask you, Galen. Can you speak to the right sizing of HVAC when builders or owners prefer to install conventional systems? Or to put that in another way, how do you think right sizing can become mainstream?
Well, it's always a challenge, right? Because a lot of equipment just doesn't get small enough. We're doing a project right now here in Virginia that the owner really wants to use less efficient heat pumps to save money, but the heat pumps that are available don't get small enough, and also they don't operate well at low temperatures, so we'd have to put in electric resistance backup heat. So, I think the industry is slowly moving in the direction of giving us smaller and smaller pieces of equipment. And unfortunately, the industry got a little bit derailed with the refrigerant change. So most of the heat pump manufacturers in the US are just scrambling to get their new equipment listed and ready for market and all that. Did I answer that question?
I think so.
Awesome. Galen, I think that if I'm not mistaken, Sarah, it looks like we've made it through the specific questions. So I just have a little bit of a follow-up one, given that we've gotten through those, and that is for people who are brand new to this world of HVAC and passive house. I guess there's two ways to address this. One is, what are the most common mistakes that you see in HVAC and passive house? That could be one way to address this. Or another one would be like, what are the most important things to keep in mind, or what is the most important thing to keep in mind around HVAC for a new CPHC?
Yeah, so I guess that metric that I talked about, square feet per ton, is kind of a good one to keep in mind, and to use it to test your contractor or your engineer, to make sure that you're not, because a lot of engineers either don't understand the nature of the quality control testing that's done in the passive house project.
Yeah.
Or they don't believe it.
Right.
And so a lot of us engineers, unfortunately, might put in the same system in a passive house that they would put in, in their last project. So if you look at that square foot per ton metric, you can say, okay, well, you're giving me a system and it has 500 square feet per ton. And so I think that's way oversized compared to what I need for this excellent passive house envelope that I have. It should be, well over 1,000, depending on the building type. But certainly for, single family residential, it could be, and also depending on your climate, but it could be, 1,800 square feet per ton. In multifamily, we find that we end up at like 1,500 square feet per ton in a lot of climates. So that's a good metric to just kind of test your contractor to see if they're paying attention. And then, some education as far as, yeah, we're going to test this, and, it's really going to be below, this air tightness metric. So you can count on that then,
That's really helpful. Yeah. And addresses one of the challenges I think that a lot of
practitioners encounter with passive house that you just identified, which is mechanical engineers who just don't kind of accept the numbers that we're showing them on passive house projects, because they're so much, the loads are just so much lower than what they're accustomed to. That's a great kind of metric to have it in your back pocket, everybody. That's cool. Looks like we had, yeah, go ahead.
Go ahead, sorry. I was just going to add that, also, look for really simple duct systems. And if it's not really simple, ask why it's not simple.
Nice.
I
Cool,
love
thanks.
asking why. I think people are almost maybe thinking about getting sick of me asking why, but it's a good thing. It's a good question. I have another couple questions that have popped in here, but Jay Waterman, you're up next if you are around to unmute and ask your question. Otherwise, I don't mind asking for you.
Yeah, can you hear me?
I can.
Yeah.
Hi.
Hi, everybody. Jay Waterman. I'm with the Portland Housing Authority, Portland, Maine. We're doing a major retrofit in a senior housing building, 120 units, 11 stories. It had zero insulation. We're adding metal panels insulated on the outside. We're using the Apoca all-in-one on those. They're studios and one bedrooms. And maybe this is a simple question, but can the APOCAs be sized up for like family apartments, 3-4 bedrooms? I think of them as sort of simple PTACs where they're just providing air to that where they're coming in, but can they be ducted to back bedrooms and that kind of thing? Or do you lose efficiency with those APOCA units in 3 and 4 bedroom apartments?
So it's important to be careful with which APOCA unit that we're talking about. They make a number of different styles of unit. One is sort of a small unit that serves one room and pokes through the wall for its intake and exhaust. The one I showed is the AIO, which is a larger unit. I think it goes up to about a ton, maybe a ton and a quarter of capacity. And that can handle, you know, a 2-bedroom apartment for sure, but you might be stretching it to get to 3 or 4. The new unit that they're just coming out with is larger than that. So it might handle a 3 or 4 bedroom apartment with some ductwork. But the small single room units are not really designed, you know, to serve multiple rooms.
That answers my question. Thanks.
Yeah.
Awesome. Alrighty, Galen, take a breath. But in the meantime, I have another question from Herman Pardon. Herman, are you still on the call? Do you want to ask your question?
It's not really a question. It was just something I wanted to add. I'm a mechanical engineer and I deal with this every single day with residential and light commercial. I would say light commercial, not heavy commercial. But one thing I just want to mention that, like with designers, with the issue that I see with these HVAC systems going in is a lot of times they're not thought about at the beginning of the project. Like, where's this stuff going to fit? You know, where's it going to go? So a lot of times me and my partner, we're trying to figure out, like, how are we squeezing this in this building? You know, the load calculations tell us how much cooling and heating the building needs. There's nothing around that, you know, to get us out of that, because that's just straight physics. So we have to provide the right equipment to cool and heat the building.
Yeah.
But just fitting it in these spaces, you know, when it's not thought about into the last minute, it makes it really, you know, nearly impossible at times.
Yeah, so Herman, what you need to do is train your architects. Train them to let you in, you know, even before they're done with schematic design, and start talking, you know, just get out a pen and sketch on their plans and say, you know, this is about what we're going to need to do. And you know, it's not, unfortunately, you know, we've been talking about integrated design for, you know, 20 years, but it doesn't happen very often. And I find that it takes us saying, no, let us in before you're done with schematic design, not after you're done with schematic design, to really, you know, get any kind of integrated feedback with the architect. So yeah,
Nice.
tell them what you need.
Thanks.
Absolutely, good points. Up next, I have Enrico Bueno. You have another question here.
Yeah, I think this 1,400 square feet per ton that you mentioned in your presentation, what kind of climate does it fit for? Is it that cold climate or is it that Seattle?
We did 1,400 square feet per ton in Kansas City, which is kind of hot and cold, but not, well, it's pretty hot, but it's not as cold as you might see. That was a little bit limited by minimum equipment size. So we would have, you know, been, had a larger number in that job if we had had access to smaller equipment. 6,000 BTUs was the smallest piece of equipment that was available at the time, and now it's smaller than that. It does depend on climate. You know, you can you can sort of figure out what's best practice for your climate and then compare that to other buildings. But you know, passive house reduces the sensitivity to climate, right? So unless you're in a really extreme cold or really extreme hot, you know, the 1,400, 1,500 square feet per ton should be achievable.
Okay.
Or I should say, obviously, building type as well, right? If you're building a concert hall, that's going to be a different scenario.
Yeah, normally the heat pumps available in the market are oversized for a passive house normally.
Yes.
Yeah. Okay. Thank you.
Awesome. All right, George, I'm sure maybe you're active in the chat still, but if you are still on the call and would like to ask your question, feel free. I'll give
I
you a-
noticed that there are YouTubes complaining about having to replace filters and that cost adding up. I'm also concerned about, you know, cradle to cradle kind of thinking, and I wanted to ask, does anyone have MERV 13 filters that are washable, or are we pretty much locked into sending these filters to the landfill, which I think some people are recommending replacing as frequently as once every 3 months?
I'm not aware of washable MERV 13 filters. I think it's a really good point. I don't feel like we as an industry have this figured out. We have a project. We found that projects in urban environments are just, you know, there's a lot of microfine particulates in the air that can be coming into these buildings. So it's definitely the right thing to be filtering them at MERV 13, probably even better than that. But it is expensive. And so, you know, it's something that we continue to look at is, you know, what's the best, most cost-effective air cleaning method to keep fresh air in the building. I don't have the answer for you on that.
Thanks.
All righty. Debbie C, are you still on the call? Would you like to ask your question? Debbie C. Otherwise, I will ask it.
She said she
for
didn't
you.
have a mic in the chat.
Ah, alrighty. All right, so Debbie's question is, if anybody knows if EFOCA is GSA approved for federal facilities.
We don't know the answer to that.
Okay. If anybody has any insight into that, maybe we can reply in the chat because that is a good question. Already, I have another question for you here, Galen. Do you have any comments on the CERV2 ERV from Build Equinox? We're looking at single family, and it has a heat pump built into it and has a true ERV core. Any comments on that one?
I haven't looked at it for a couple of years. When we looked at it before, we found the capacity too low for the projects that we were working on. But I think that was the first generation unit. We haven't looked carefully at the second generation unit. So we need to reevaluate that.
Interesting. All righty, Sean Santamora, would you like to unmute and ask your question? If you are still on the call with us. Otherwise, I will ask Galen right now. Galen, mechanical rooms. Should the mechanical rooms be designed before? Oh, this is kind of a little bit more of a comment than a question, but for everyone's sake, mechanical rooms should be designed before the kitchen and the master bedroom. Man, what a world that would be. Where does the brain and the lungs of the house go? Is what I'm always asking too.
Yeah, train your architects.
Train them. Alrighty. Since that was kind of more of a statement, let's just round it out with one more question that I have for you. This is regarding that 1,400 square foot per ton. Is that only for single/multifamily, or residential, or does that apply as well to something like a veterinary clinic or something similar?
No, yeah, a building like a vet clinic would be completely different. We actually did a passive house animal hospital, and those kinds of buildings are all about the ventilation air. And it's because there's just so much ventilation air that you put through them like you would in a hospital building. Also, buildings with really high density occupants, like a concert hall or something like that, that rule of thumb would not apply.
I have one more question that's trickled in here. If you all have anything else, now is the time to throw them in. Otherwise, please feel free to connect with Galen. Alrighty, this is a fun one. I'm sure we're all very interested in how is AI helping in the efficient building space? And this is a question for you, Galen. Galen, you cannot ask ChatGPT to answer this one for you.
I was going to ask if there's someone else on the call that can answer that. I'm a little bit of a Luddite. I haven't powered up ChatGPT yet myself.
Good.
I can only speculate, but given how critical information flows are in high performance building design and delivery, with there's just so much information to move from different practitioners and to manipulate and to optimize. I can't imagine that AI won't play a major role moving forward. It just seems like our industry is ripe for it, really. And that's exciting and scary. I think all of us can probably feel both.
Oh, absolutely. Absolutely. I know at least for like manual J and calculations like that, there's already things that'll kind of just, throw up the data for you. So I'm interested to see how the AI starts to kind of take those things and, take whatever other contextual things you want to input and start to work that in. How interesting. All right,
Yeah.
one more. Oh, go ahead,
And well, I was just going to say that if people have any specific experiences with AI, like you just mentioned, please share them in the chat. I think it'd be really interesting to start learning about applications of AI in our world. So, great question.
Oh yeah. All righty. I have one last question. Laura, would you like to round us out with your question, or would you like me to ask it?
No, I'll ask it. Hey, Galen.
Great.
So, we have, as you know, heat pump hot water heaters. Ours has the condenser in the unit. And so we have a very cold basement. We have a vent to the room above. Should we put a little fan there to try and capture this coolth? And if so, what size or little fan would help make use of this transfer of exchange that would be more efficient?
I think that's a good idea. Yeah. And I believe that those heat pump hot water heaters are like between 175 and 250 CFM, something like that. I think the only thing that you have to be careful of is that you don't overpower the fan in the hot water heater. Like I wouldn't duct it directly from the hot water heater, maybe take it from like right where the cold air is coming out, because otherwise you might mess up the fan in the hot water heater.
All right. And what little fan, so a fan that's 175 to 250 CFM. Is that what you're saying?
Yeah. Fantech makes some great little fans like that.
Okay. Fantech. All right. Great. Just trying to, I always wonder who's going to invent the refrigerator connected to the hot water heat pump so that they can be an exchange there. That would make a whole lot of sense.
Totally. Yeah. I fantasized about having heat transfer fluid running around your house, taking heat from the refrigerator and, putting it into your hot water heater or whatever other device. That would be an engineer's dream.
Thank you. Great presentation.
Thanks, Laura. Good to see you.
All right, that's awesome. everyone had some really great questions. Thank you guys for thinking about things and asking. Galen, I just want to see if I can pick your brain real quick on a really specific thing that you had mentioned once, which was an AC that you had maybe not looked at lately. Do you know what the name of that AC was? Otherwise, maybe we can reference the slides and whatnot when they come out.
Oh, the sort two, is that what
It
you're
might
referring to?
be. It might be. Just asking on behalf of Mike. But Mike, if that's
You okay?
Okay.
if that was not necessarily the answer you're looking for, Mike, please feel free to check back on the presentation when it becomes live in a couple days. Otherwise, thank you all. We know we kept you a little bit later, so thanks for hanging in there with us. Please feel free to check out some of the links that Kara has dropped in the chat and stay tuned for some of those awesome events coming up.
Thanks,
Thank you,
everybody.
Galen. Yeah, awesome job, Galen. Really appreciate you bringing it to all of us.
My pleasure. Thanks,
Yeah.
everybody.